Good morning, geometers, and welcome back to another video lesson with Mr. Forster. Today we'll be going over our third lesson in Unit 6, which is perpendicular and angle bisectors. So let's go ahead and get started. Starting off with our perpendicular bisector, and again, all of these resources are also available in your textbook. This is in the textbook lesson 6.1, or chapter 6, lesson 1 in the textbook. We have our perpendicular bisector. And again, just to define what is a perpendicular bisector, it is a line that is perpendicular to a segment at its midpoint. So you can see over in our diagram down in the bottom left, let me grab my highlighter here, laser pointer rather. We have CP, which is this line here, is it's kind of hard to see here, but the upside down T symbol means perpendicular bisector of segment AB. And you can maybe see these two tick marks here as well. So A to P and P to B are equal length because P is that midpoint. And again, perpendicular, just as a reminder, means that these two line and line segment combo will meet at a right angle. Next, we have the perpendicular bisector theorem, so something that we can conclude from when we have a perpendicular bisector. And it says that if CP is the perpendicular bisector of AB, just like we had in our previous slide, then what happens is that these two segments, if I connect a segment from A up to this point C here, and another segment from B up to this point C here, that these two segments will be equal in length. So let's mark that appropriately. Let's grab our pen. So these two are going to be equal in length. We can prove this perpendicular bisector theorem is true. So if we start off, we have here again that CP is the perpendicular bisector of AP is the given statement here. Let me grab my laser pointer. So here's our given statement. Again, starting off similarly to how we started last time. Quick side note, this diagram is above this table in your notes. I just added this to make the slides go a little smoother as I was making the video. So if you're looking for this in your notes, you don't have to redraw this. You should have this same diagram just above in your notes here. All right, let's go ahead and go through our proof. So the first thing, as usual, is we can take the given information and we can use that as our statement, and our reason is it was given to us. The next thing we can do is we can say, okay, well, CPA and CPB are both right angles. So let's draw that in over here. So CPA is going to be here, and CPB is already drawn in, but we'll add the red here to make it stand out. So these are both right angles, and the reason for this is the definition of what it means to be perpendicular. And then we can claim, okay, these two angles are in fact equal to one another, and the reason for that is all right angles are congruent. Next, we can use AP and BP, their lengths being equal. This is the definition of a bisector. So we have the CP is a perpendicular bisector. So because of the nature of a bisector, we can say that these two things are equal. Next, we have that CP will be congruent to itself, and that again is known as the reflexive property. So the reflexive property gives me that CP is equal to CP. And now you may notice, based on our practice from our semester 1 review, we have our side angle side property that we can use for our triangle congruence. And then finally, if we want to claim that CA and CB are the same, well, they are corresponding parts of congruent triangles, so they will be congruent, which is our CP-CTC. I'll leave it up on the screen here for a moment for you to catch up, but you can also pause the video at any point in time. All right, moving on. Our third concept here in this unit, or this lesson rather, is the converse of our perpendicular bisector theorem. And so much like before, our converses are going to reverse the logic. So we're going to start with where we began last time. It says that if DA is equal to DB, it might be a little bit hard to see here, but there are some tick marks here and here. Then point D lies on the perpendicular bisector of AB. So what that means is if we were to extend CP here all the way down, my best to go through that, it would be on that same line. A couple of practice problems here I want you to try on your own. So go ahead and pause the video. All right, so if you haven't paused and tried these on your own, please do so. Otherwise, if you have paused, then let's go ahead and go through the answers here. So for part A, for finding the value of RS, we have this perpendicular sign here, and we have the fact that RP is being cut into 2 equal parts. That means that SQ is the perpendicular bisector, which means that SR will be equal to SP, which means that SR, or RS rather, is 6.8. Moving on to part B. In part B, it's looking for EG, which is going from E all the way to G. Again, I have perpendicular here. I also have that this length 24 is equal to this length here. So that means that FH must be the perpendicular bisector. So I can fill in that E to F is going to be the same as F to G. So let's go ahead and do that. So this is going to be 9.5 as well. And if I add these two things together to get the full length of EG, then I should get 19. All right, part C requires a little bit more work. We've added some algebra into our mix here. So let's look and see. We've got our perpendicular bisector again. I know it's kind of hard to see, but hopefully on the printed version for you all, or if you're looking at it at home on the PDF, it's easier to read. Those two segments are congruent. We also have our perpendicular symbol here. So I have the perpendicular bisector BD, which means that those two expressions, 3x plus 14 and 5x, will be equal to one another. So since these two things are equal, we can set up our algebraic equation. We can then subtract 3x from both sides to get 2x is equal to 14. And then finally, if we divide by 2, we get x equals 7 to solve for our variable. Now, keep in mind that we're not asking for what the variable value is, we're asking for what the length of AD is. So we've got a little bit more work to do. All right, substituting our x equals 7 back in, we can take AD is going to be equal to 5 times 7. So that's AD was 5x, which means that AD is equal to 35. All right, finally, number 5 asks, can we conclude that AB is equal to BC? And if not, what other information would you need to be given? So in this case, no, we cannot make this conclusion. We would need to know that BD is perpendicular to AC. BD, that segment is bisecting AC, but if it's not the perpendicular bisector, then we don't have enough information to make this conclusion. All right, so our second theorem and its respective converse here is the angle bisector theorem. The angle bisector theorem states that if AD bisects angle BAC, and a reminder, angle BAC is this angle right here. Let's grab my pen again. Angle BAC is this angle here in red. We need some other things though. It says and BD, or DB rather, that segment is perpendicular to that ray AB, so this needs to be true. And we also need the case that DC and this ray AC are also perpendicular, so we need that to be true as well. Then we can make the claim that DB is equal to DC. So we can make this claim here that this segment is congruent to this segment. All right, number 7, the converse of this, again, if we reverse the order of our logic here. So this time we're given that those perpendicular pieces are there. So DB is perpendicular to AB and DC is perpendicular to AC. We're also given that DB is equal to DC. Then it will say that AD will bisect angle BAC. So let's do this in a different color. Let's use some purple here. So that means that this smaller angle will be equal to this angle here. All right, let's look at some examples and apply this. So in number 8, as usual, I want you to pause the video and try on your own. All right, hopefully you've already paused and tried. If not, let's go ahead and go through these together. So for part A, we're given a few things. We're told that we have the perpendicular here and here. So that takes care of one of our requirements. We also have that this 7 here is equal to this 7 here. And if we have this scenario where we have these two perpendiculars and we have these two segments that are equal to one another in this exact setup, then it means that JF has to be the angle bisector. So that's our angle bisector converse in this case, which means that this angle is going to be equal to this angle. So angle GFJ is going to be equal to 42 degrees. For part B, this time, and it's kind of hard to see, but there are some symbols here and here that show us that we have the angle bisector. We also have the fact that this is perpendicular, which means we can conclude that these two segments, 5x and 6x minus 5, must be equal to one another. So 5x in red, 6x minus 5 in blue. Set them equal, and then if we subtract 6x from both sides, we would get negative x equals negative 5, and then we would get that x equals 5. Now, again, keep in mind, it's not asking for the value of the variable, it's asking for the length of the segment RS, so we've got some work to do to substitute in. RS will be equal to 6 times 5 minus 5, and then that means that RS is equal to 25. All right, moving on to our real-world scenario. It says here that a soccer goalie's position relative to the ball and goalposts form congruent angles as shown. So it's kind of hard to see, but there are some symbols down here. This is congruent angle there, congruent angle there. It says, will the goalie have to move farther to block a shot towards the right goalpost or the left goalpost? So take a moment, think about it, and then I'll share with you my answer here in a few seconds. All right, I'm curious, which did you come up with, the left or the right? Here's what I came up with. The congruent angles tell us that the goalie is on the bisector of angle LBR. This means that the goalie is the same distance from both of the segments BR and LR by the angle bisector theorem. So the goalie actually would move the same distance to block either shot. Bit of a trick question here, but that's all right. Sometimes us math teachers do that. All right, our last type of problem is we're integrating some of our algebra skills back in, especially with writing equations of lines. So I've given you some helpful hints up on the screen already. So I've given you the midpoint formula. I've given you the perpendicular slope is the opposite reciprocal, as well as the formula for slope. And then our most common linear equation or line equation is y equals mx plus b, often called the slope-intercept form. So I want you to try this on your own, see if you can put together how you would do this. I've given you kind of some pretty heavy hints here on what you would need, but I'm going to go ahead and let you try this on your own for a moment, and then in a few seconds I will share my solution. All right, hopefully you weren't too frustrated by this one. I know it's a lot of moving parts here, but first we need to find the midpoint. So just to give a little bit extra hint, and you can pause after I say this if you want to try again. A perpendicular bisector, again, is defined by the fact that it is both perpendicular, so it has the perpendicular slope, but it also goes through the midpoint, so it has to pass through the midpoint. So the midpoint is going to be on the line itself for that perpendicular bisector. Okay, so again, if you want to pause with that hint and try again, feel free to do so. Otherwise, let's go ahead and look through the solution that I have here. So again, using the midpoint formula, x1 and x2, let's go ahead and write those in. So I have x1 and y1 here, and then let's use a different color for x2 and y2. Let's use red. And then we have, at least the way that I set this up, I went from left to right, x2 and y2 here. And using this, if I plug these things into my midpoint formula, I'm using MP to stand for midpoint, then I have x1 is negative 2, x2 is 4, so I'm adding those together and then dividing by 2, and then same thing for y1 and y2, which is 3 and 1 respectively. So when I do that, it simplifies to 2 over 2 and 4 over 2 when I do the addition in the numerators. And then finally, if I simplify a little bit further, my midpoint is at the point 1, 2. So I know that my perpendicular bisector has to pass through this point. I just don't know what the slope is yet. So we can use our slope equation to figure out what our slope is. Again, I'm using the same y2, y1, x2, x1 from my points P and Q up above. And I'm going to plug these values in. So I have 1 minus 3 in the numerator for y2 minus y1, and 4 minus negative 2 for x2 minus x1. Simplify a little bit and I get negative 2 over 6, and then simplify a little bit further and I get negative 1 over 3. Now this is the slope of the line PQ, or the segment PQ. It's not the slope of the bisector yet, because I need the perpendicular bisector to be perpendicular. And so this is where this term opposite reciprocal comes in. Opposite means the opposite sign, so I'm going to take this from negative to positive. Reciprocal means I'm going to take this fraction and make it its reciprocal, which is like flipping it upside down. And so my new perpendicular slope is going to be positive 3. So 3 over 1 can be written as just 3, and negative changes to positive, so I get a perpendicular slope of 3. Now I have all the things that I need to actually write the equation, and so I'm going to go ahead and do that. I'm going to substitute in some values. You'll notice that I'm using my midpoint as the point that I put in for y and x when I go to solve for b, and the reason for that is the perpendicular bisector does have to pass through the midpoint. It doesn't necessarily pass through, in fact it won't pass through these 2 points up here, so if you use one of these two, keep in mind that it's passing through the midpoint, not the end points. And then if I solve for b, I would get negative 1 is equal to b, and then finally I'm going to write this out as the equation without the values of x and y, but just as variables for x and y. So I have y equals 3x minus 1, and this would be your final solution to this particular problem. So again, lots going on here, lots of moving parts, but putting some of these concepts together and practicing some of our algebra review skills at the same time. So if you have questions, please ask them of myself or Mr. Swatala in class. Again, we like answering questions, believe it or not. Crazy that we got into this whole teaching thing to like help and be teachers. Weird. All right, moving on to our final slide. I'm not going to go through step by step as I did before. If you want to see the full worked out version, you can go back in the video and rewatch part A. But I'm going to share with you just the solutions. So again, I'm going to have you pause here, try this on your own as best you can, and then I will share with you the solutions here in a few moments. All right, going from left to right, the midpoint that I got for these 2 points was at 1, negative 3. The perpendicular slope, well, the regular slope rather, of the segments is 1, and that means the perpendicular slope would be negative 1. And then if we take that 1, negative 3, and the perpendicular slope of negative 1, and if we solve for b, we get that y equals negative 1x minus 2, or negative x minus 2 would also work as well. All right, geometers, that concludes our third lesson of Unit 6. So thank you for making it all the way to the end. As usual, make sure you check in with either Mr. Swatala or myself if you have any questions. In my class, at least, I know the following day after this video gets posted, I'll have some time in the beginning of class, but you can always email me at any time to ask questions about things. So check in with your teacher about what the assignment is to go along with this. Again, if you're in my class and you're accessing this, then you're already where all the homework problems are, but I'm not sure exactly how Mr. Swatala has his set up. But yeah, hopefully you're doing well with our second half of geometry so far, and I will catch you in the next one.